go to section 2. We're going to talk about combinations. We kind of touched on it a little on Friday, but a combination is a selection of R objects from a group of N objects where the order in which you choose is not important. The order is not important. Again, this is why a combination lock is so poorly named. The order is critical. And combination formula is very similar to the permutations that are distinguishable. And so if you look at our formula here, and we cover up the r factorial on the bottom, so we have n factorial over n minus r factorial, that's permutations. What we're then doing is dividing out all the repeats of the group of objects that you're selecting. How many different ways can the same objects be chosen in different orders? That's what you're dividing out with the r factorial. So if we have a deck of cards, for example, and we'll refer to deck of cards a lot, I know that there's a few people out here, and you could be one of them, who don't have a clue what's in a deck of cards. If you're one of those people, on page 690, if you're not familiar with what a deck of cards has in it, page 690, bottom right-hand side of the page lists out there's 52 cards in the deck, 4 suits, clubs, hearts, diamonds, spades. Each suit has 2 through 10 integers on a card, and then they have jacks, queens, kings, and aces. Cards that are considered face cards. How do you know if you have a face card? It has a face on it. Aces do not. Aces do not have faces. Threes do not have faces. We're looking at cards like this that have a face on it. This is a king, if you're not familiar with these. Okay? In a lot of card games, poker for example, you get 5 cards dealt to you. If we wanted to know how many ways can you choose 5 cards from a deck of cards, how many ways can I deal you 5 cards? It's 52 combinations taken 5 at a time. This is NCR, not NPR, because we don't care which order you get the cards. We do not care which order you get the cards. So if you get dealt 5 cards, in whichever order they come to you, and these are the cards you get, and you're playing poker, you're hoping you can keep a straight face. Okay? This is a good hand. Yeah, straight flush, royal straight flush. This is pretty impressive. You're going to win. Okay, there is no way you're not going to win. You are going to win. The question is, how much can you get other people to think you're not going to win? All right? How many ways are there to get 5 cards dealt to you? Well, that's combinations, 52 taken 5 at a time. That number is almost 2.6 million. Now, you want to be able to use your calculator to do this. This first line right here is not negotiable for me. 52 factorial, 52 minus 5 factorial, and 5 factorial. Okay, so here's a class, a government class, say, 6 seniors, 5 juniors, 4 sophomores, 3 freshmen. How many ways can you make a committee that has 2 seniors and 2 juniors on the committee? 2 seniors, 2 juniors on the committee. We're trying to make groups of 4. If you're trying to make groups of 4 students, what do you have to take into consideration? What's the issue in this problem that's different than the last problem?
We're doing all.
What does all mean?
You're taking into consideration all the classes.
Yeah, oh, you mean all the kids in the class?
Well, all the 6 seniors. And
Those are kids in the class, right here.
Oh, yeah.
These are the kids in the class,
Okay.
so they're all eligible to play.
The problem is you can't make it for all 4 groups. The groups would be perfect for us.
So, what do I need to do?
So one of the groups need to be 2.
Okay, what else? What are you referring to?
When you add all those together, the number's not divisible by 4.
Oh, that doesn't matter.
Oh, okay.
Yeah, that's okay. But you're on to the right. This is the problem. What is causing the problems?
Well, it says at most 4.
What does that mean?
It could be a group of 2 or 3.
Or,
1.
yeah. So this right here, at most, that's the catch. So there's no way to do at most 4 in one shot. So you have to break it down, and you have to say, I need to do committees that have 4 kids, committees that have 3 kids, committees that have 2 kids, and committees that only have 1 kid. I don't know how that's a committee, but that's what you need all 4. Okay? Is anyone not seeing how to get that number?
Where'd you get the 18?
From the students in the class. 6 plus 5 plus 4 plus 3. You have 18 kids to choose from. Is that right? So you have 18 kids to choose from, and we want a group of 4 to make that committee. How many ways are there to make a committee of 3? Only 816 when you go to a committee of 3. Committees of 2? 153. And committees of 1? 18. Altogether, you add up the different committees, and there's 4,047 different committees of at most 4 students from this group. 4,047. When you get at most, or at least in a problem, then you have to do each circumstance individually and add them. So if you said at most 4, or at least 4 on a committee, what would you have to do for that? What's that? Yeah, you'd have to do everything. 4 on to 18. 4 plus 5 plus 6 plus 7 plus 8. I won't do that. It's not going to happen. If I wanted to do it at least, I would say at least 14. And you have to do 4 or 5 different combinations and add them. Some things you need to know. Combinations of 0 items taken 0 at a time is 1. There's only one way to take nothing from nothing. Combinations of 1 item taken 0 at a time, or 10 items taken 0 at a time, or any number of items taken 0 at a time is 1. And combinations of 1 item taken 1 at a time, there's only one way to do that, or 5 items taken 5 at a time. There's only one way to do that. So the combination of n items taken n at a time is 1. And by definition, n factorial, when you have n equals 0, 0 factorial by definition is 1. 0 factorial by definition is 1. My history of that, my knowledge of that, I believe it has to do with the number of ways to arrange 0 items. So if you have, how many ways can you arrange nothing? Well, there's only one way to arrange nothing. Okay, so these things you want to keep in mind right here in the circle, combinations n items taken none at a time, there's only one way to do that. And n items taken all of them, n taken n at a time, there's only one way to do that. Remember, the order doesn't matter. It's a combination, not a permutation. Everybody good here? Combinations 10 items taken 15 at a time. Can't happen. We can't take 15 from a group of 10. Anytime you're doing r greater than n in a combination, there's no way that can happen. If r is greater than n, it can't happen. So anytime you're trying to choose r items from n items, and r is bigger than n, there's no ways that it can happen. Should you write 0 or should you write no solution? 0. It's asking you how many ways. The answer is there's 0 ways, not no solution. It's not a no solution. We know it can't happen. What's this all about on the right? What's this? Pascal's triangle, right? We did that a while back, maybe chapter 3, or it's been a while. So you might want to go back and visit it. Remember, you start with the triangle of ones at the top. And then we do the diagonals. So like the 1 and the 2 combine to give you 3. 2 and the 1 combine to give you 3. And all down the edges are 1s. All right. Pascal's triangle are also the values for combinations. Combinations, 3 taken 1 at a time, 3. Combinations 3 taken 2 at a time, 3. Combinations 3 taken 3 at a time, 1. Combinations 4 taken 2 at a time, 6. Now, why you would use this with modern technology, no idea. You have a calculator that does NCR for you. You're welcome to use Pascal's triangle. It's faster than your calculator if you have it written out. What you need to remember is row 0 for Pascal's triangle is the top row, row 1, row 2, row 3. The second number in the row tells you what row you're dealing with. So the second number, this is row 4. The second number is a 5, that's row 5. Okay? And you start with combinations 5 taken 0 at a time, 5 taken 1 at a time, 5 taken 2 at a time, 3 at a time, 4 at a time, and 5 at a time. And that gives you the value. Binomial expansion. When we take a binomial and raise it to a power n, you generate a polynomial with n plus 1 terms. We've done this before. These are probably the same notes from chapter 3 whenever we did this. And these numbers right here can be written with combinations, or you can just use the coefficients from Pascal's triangle. I don't care which way you do it. I just use Pascal's triangle. I don't get all that worked up over this. So when we expand binomials like a plus b to the 4th, which we did back in chapter 3, your Pascal's triangle coefficients are 1, 4, 6, 4, 1 from the power of the 4. And then the first term times the second term, and then the powers on the first term start with 4 and go to 0. The powers on the second term start at 0, go to 4. And then we simplify. There's only 2 reasons why people screw up Pascal's triangle, or binomial expansion with Pascal's triangle. They use the wrong row of Pascal's triangle, or they can't do the simplifying with the powers correctly, which is the most fun. So you have a plus b to the 4th, it's 1, 4, 6, 4, 1, and then a to the 4th, a to the 3rd, a to the 2nd, a to the 1st, b to the 0, b to the 1st, 2nd, 3rd, and 4th, and then you simplify. obviously, this is pretty basic. So if we look at one that's a little bit more complicated, like x minus 3y raised to the 5th power. Remember, we're raising to the 5th. That means x minus 3y times x minus 3y times x minus 3y, etc. Every couple of years, I get a student who will actually multiply them out. Talk about them getting sand from rocks. I mean, you need a bucket of sand for your kid's little turtle in the backyard, but you don't have any sand, so instead of going and buy sand, you bought rocks and a hammer. That's what you're doing right here. This is pain and suffering. Okay? Which row of Pascal's triangle do we use? Row 5. Second number in the row is a 5. Now this one's a little tricky because of the minus, but this is how it looks. Pascal's triangle, row 5 is in blue. Because of the minus between the two terms, the first term, 1, the 1 is positive, then it's negative on the 5, positive on the 10, negative on the 10, positive on 5, negative on 1. We just alternate, but the first term is always positive. Here. The first term is x in the binomial, so every term or every spot here has an x. Each term in this expansion has an x. Starting with power of 5, then going 4, 3, 2, 1, 0. The second term is 3y. I put it in parentheses so I don't screw up the simplifying. I did it in green, raised to the power of 0 in the first term, then increasing 1, 2, 3, 4, 5. Notice I don't worry about this negative is not with the 3y, it's just negative in between the two terms. That's what made it go plus minus, plus minus, plus minus. Oftentimes we forget and people will make this a plus. I didn't say the first sign is positive. I said the first term is positive. So then it's minus, plus, minus, plus. Questions? If it's easier to think when there's a minus in here, the first sign is minus. That makes it easier for you. And then alternate. Great. Do that. So if you would rather think, okay, first sign is going to be the minus, and then we alternate, that works good too. This is where I lose students. They want to go right to the answer and they don't want to put in an intermediate step. I usually have this step first. And this step usually is simplifying the term 3y to the power. In this case, that's a 1. This is 3y, easy to multiply here and get 15x to the 4th y. But here, I don't want to do this in my head and get 9y squared times 10. I'm going to write it down. And then I usually don't have an error in my answer. But I'll get a half a dozen or so who, I don't want to write this down because I'm just going to go from here to here, and they screw it up. They're usually little arithmetic mistakes, avoidable with 3 more seconds worth of work, 10 more seconds, whatever it is. And then your final answer, go right here. Is everybody good on how to expand the binomials? Is everyone clear on where we got the coefficients, where we got the reds and the greens? The reds and the greens and the coefficients in blue. Anybody not clear? The coefficient part I get from Pascal's triangle. So go to the power here, you get a 5. Go back to Pascal's triangle, which I have right here, and we go to row 5. 1, 5, 10, 10, 5, 1. Okay, do you know how to generate this? Okay. So when you get to row 5, second number is a 5. We take those coefficients, and that's the first thing that went down in blue. The second thing I did is I put minus here, then plus, minus, plus, minus. Then I took the red X and I put it in all of these spots with the power of 5, then decreasing to 0. And then I took the 3y in parentheses and started with the power of 0 and increased to 5. Notice the sum of the powers, red and green, are always going to add up to 5. The power of the binomial. That will always be true. Somebody else have a question that I missed? Okay. So now what we're going to do is we're going to draw 5 cards. We're going to deal you 5 cards. And we want to know how many ways could you have a hand of 5 cards, just 5 cards at random, in which you have at most 1 queen. Here's my hand of cards. Is this a winner here? Is this going to satisfy at most 1 queen? No? How many queens are there? How many? I'm not trying to trick you. How many queens are there? There are no queens. So is that not at most 1 queen? Okay, tell me how many queens you would have to be at most 1 queen. How many queens could you have? And 4 is not at most 1. 1 would work. What else would work? 0, right? If I have no queens like this, Jack 7, King, King 8, that's at most 1 queen, right? No queens is at most 1 queen. See, they're messing with you. Now, if I said at least 1 queen, then I could have 1 queen. What else? 2 queens, 3 queens, 4 queens. You can only have 4. They don't fall for that trick either. Maximum 4 queens, but this says at most 1 queen. So we could have no queens, and we could have 1 queen. Now, you're going to do this wrong, and I don't want you to go far with it. So I don't want you to write down how to find at most 1 queen and do the number of ways to get no queens. Because I would be willing to bet that almost everyone in the room would write it down wrong for no queens. How many ways are there to do no queens?
1.
No, I want you to write, taking 5 at a time. Why 48?
Because you're taking queens out of the deck.
So we're choosing, if we're going to get no queens, they can't be in the group you're choosing. Even though they're in the deck when you're dealing them. We're trying to figure out how many ways can we get a hand of 5 cards with no queens. There can't be a queen here to choose from. So you have to eliminate them from the possibility of being chosen. So there's 48 cards, taken 5 at a time, which is 1.7 million ways. You could get 5 cards without a queen in your hand. Okay. Now, what if you wanted to get a hand that had 1 queen exactly? Again, this is a little bit tricky. How could we do 1 hand exact, 1 card queen, and the other card's not queens? How many queens are there to choose from? 4. How many do you want? 1. So the first part of this is going to be 1 queen is 4 taken 1 at a time. And you're going to multiply that by 4 non-queens. 48 taken 4 at a time. This little notation that we have going here, right here, I almost always do that because I need to keep my head straight with exactly what is it I'm looking for here. Here I'm looking for 1 queen. Okay? So from the 4 queens, I'm choosing 1. And then what about my other 4 cards? Well, I want them to be not queens, so I choose them from the 48, taking 4 at a time. I want 4 of those, and I want 1 that's a queen for a total of 5 cards. I need to see this written out right here. I still have people who, I don't want to do that. If you don't put this, you're going to lose points. A lot of them. Okay, I don't have a problem with you using the NCR button, but I want you to have written out what you're doing with the NCR button. So there's 4 ways to choose your one queen. 94,500 and way to get 4 non-queens. When you multiply them, 778,320. Different hands that have only one queen. And we know that there's 1.712304 million where you don't have any queens. So how many ways are there to get at most one queen? What would you do? Add them together. So the 1.7 and the 778,320. Now I think we already did this, maybe we didn't. How many 5-card hands can you have when you're dealing cards? If you were going to take a deck of cards and get 5 cards dealt to you, how many 5-card hands are there? This 2.6 million approximately is all possible 5-card hands that you could have. There are no other outcomes that can occur when you're dealing 5 cards to a person. It's got to be one of these 2,598,960. Here's why I'm telling you that number is important. A lot of times they ask about 5 cards, like for example here, at most 1 queen. And you have to do 0 queens and 1 queen. Well, when you add up your situations here, the 0 queens plus 1 queen, you can't go over the 2.6 million. If you do go over it, you've done something incorrectly. You've done something wrong with one of your situations because they can't go over. You can't overlap 0 queens and 1 queen. You can't have all these situations get you more than the 2.6 million. Okay? So 5 different cards. This is the total number of outcomes. So if you're doing a problem and you have to do multiple situations and you add them up and you end up with more than 2.598, you got a problem. Let's see if you can do 5 face cards. How many ways are there to get 5 face cards? 12 combinations, 12 items, taken 5 at a time. There's only 12 face cards to choose from. You want to figure out how many ways can I choose a different hand that's all face cards. So that's 12 factorial over 12 minus 5 factorial times 5 factorial. Again, I don't need you to go any further computation-wise. I don't need you to figure anything out. I don't need you to do 12 minus 5. I just need you to do the NCR button at this point, if you're so inclined. How many ways are there to do 12 taken 5 at a time? 792. Remember, order doesn't matter. Order doesn't matter. The order in which you got the cards is not important. Okay, we're going to spend today working on this part of your assignment. I don't want you to spend much more than an hour on this total if you need to spend that much time. If you get home and you've worked at home for maybe 40 minutes, you should probably stop. And then you'll have time in class to work some more, but I'm also going to give you more work tomorrow. This is just combination and binomial expansion. Okay? But don't spend much more than an hour altogether on this assignment if you